Okay, so we're just going to do one set of flip notes on nuclear chemistry, just to expose you to a couple of the different ideas behind it. So looking at these reactions here, these are ones that we've seen. These are the types that we've done. So we can recognize that this is a double displacement. In fact, it has a precipitate involved. Which one of these two would be the precipitate? See if you can identify it. It would be this one here. And we can look at this one here, and we have a single replacement reaction. Okay, so those are two that we are very familiar with. But this is a little bit different. This here involves, you have to have the mass number and the atomic number, and it involves changing the elements. So up until this point, we've really only addressed that elements have to stay exactly the same on both sides of the reaction. That is true 99% of the time, but there are a few nuclear reactions that do change the nucleus, and so we can change from nitrogen to oxygen in a nuclear reaction. In order to do that, we need to review this quickly here. We need to make sure that we know that that top number is the mass number. We learned that way in the beginning of the year. That's number of protons plus the number of neutrons. We also need to know that this bottom number here is the atomic number. That's the number of protons. We know that this is the top number here on the periodic table. And a lot of times, because it's hard to do this typing, it is usually written directly above each other. You'll see, because of the need to type things, it doesn't work out that way typed, but I think you guys can easily translate it into something like that. And then this word of isotopes, which we should know, is that atoms of an element that differ in the number of neutrons. Okay, so that's where this mass number is going to change. This atomic number can never change. We don't always write it there, but in nuclear reactions we do, because it really helps us balance the equation. Okay, so looking at an example of a nuclear reaction, we can see that the math works out correctly. Okay, so if we look here, 14 and 4, if we add our top numbers, 14 and 4 is 18. And if we add our top numbers here, 17 and 1 is 18. So those top numbers need to be conserved. Again, if we add the bottom numbers here, 7 and 2 is 9, and 8 and 1 is 9. We change what element it is based on what number ends up here in our problem. So 8 is the atomic number for oxygen, and 1 is the atomic number for hydrogen. So nuclear chemistry is the branch of chemistry that deals with nuclear reactions, and it changes the atomic nucleus. Okay, and I'll show you how to write these reactions. It's pretty straightforward. A radioisotope is an atom having an unstable nucleus. We've learned that a lot of these are the ones at the end of the periodic table. And that radioactivity is the spontaneous disintegration of the unstable atomic nucleus with the accompanying emission of radiation. So we know certain elements are radioactive, and a lot of those are much heavier elements at the bottom of the periodic table. So these are our 4 types of radiation, and this is the thing to really be familiar with. We have 4 types. They're pretty straightforward. They're always the same. Alpha, this is the symbol for alpha, and then this is what it is. It's a helium molecule. So 2 neutrons, 2 protons. It's 2 plus 2 because it's protons plus neutrons. The charge is plus 2, okay, and it's a helium nucleus. We have beta radiation. The symbol is the B, and it's 0 because it's an electron. Electrons don't have any mass associated with it. It changes the charge by -1, and it's an electron. A positron is a particle that we haven't really talked about, but it's used in nuclear radioactivity because it allows us to change the nucleus by a +1 charge. And then we have gamma radiation, which is just high energy electromagnetic radiation that doesn't fall into one of those other 3 categories. So the rules for writing equations with nuclear charge: the mass number is conserved, just like I showed you 2 slides ago, and the electrical charge is conserved. So all of those stay conserved and stay the same. And so we'll try some of these right here. So nuclear equations. So transmutation, we change one element into another. And we're going to start with an alpha emission, which means we're going to give off a helium nucleus. So if we look here, we're starting with polonium here, We give off this helium nucleus, and this is what's left. If we check our math, 207 plus 4 gives us 211. 82 plus 2 gives us 84. And so here's one for you to try. So take a second and see if you can complete it. It is an alpha emission. So we know that this part here will be 4, 2, HE, and then we just need to do the math. So this is 86. There's 2 already here, which is going to make this 84. This is 219, which is going to make this 215. But then I need to change the element. So I have to look up on the periodic table what element is 84. Happens to be polonium, which is right here. And I'm going to put PO. If we look at beta emission, we take a beta particle, and if we admit a beta particle here, if we look, this is 210, and this is 0 and 210, so those are equal, and this is 83, so this must have been 1 higher if this is minus 1, so this is 84, and that's how we change what that element is. So here's one for you to try. Again, it's beta emission, so this is going to be 0, minus 1, E. And if this is 87, then this must have been 88. This is going to stay the same at 223. And then we have to look up what element is 88, and it's 88. Okay. Positron decay is giving off a positron. If we look, we have 6 here, and plus 1 and 5 is 6. We have 11 here, and 0 and 11. Okay. And then we have K capture, or electron capture. And so we have where this is going to be a reactant. Okay, so instead of decaying, where we're producing things, we're capturing, which means we're bringing it on. So 100 plus 0, that gives us 100. 46 minus 1 gives us 45. Here's one for you to try. It's rubidium. We're still going to capture. And we're still going to do the math. So this ends up being 36. This ends up being 83. And element 36 on the periodic table is krypton. If we look to do half-life problems, which a lot of times math covers, so you guys have already been exposed to this sort of half-life problem. And in fact, I think in math you do some that are even harder than what we do. It's the length of time necessary for 1/2 of an amount of a radioactive nuclide to disintegrate. So we take the original mass times 1/2 to the x, x being the number of half-lives, and that's going to give us the final mass. So let's see what that type of problem would look like. It's pretty straightforward, and we're not going to get into the logs and everything that you might in math, because you actually might do harder problems with half-life in math. So the half-life of barium-131 is 12 days. How much of a 50-gram sample will remain after 36 days? Well, first you have to figure out how many half-lives that is. So 36 divided by 12 gives us 3. So if we have 3 half-lives, it's 1/2 to the third. If it's 1/2 to the third, we're going to take our original 50-gram sample and multiply it by 1/2 to the third power, which is going to equal x. And x ends up being 6.25 grams. If you're not sure how to put that into your calculator, please make sure you ask somebody. You can put in the 1/2 in parentheses and then use the caret and then 3. Or if you're ever really stuck, you can do, 0.5 times 0.5 times 0.5, which I know is a little cumbersome, but at least you know you're getting the right answer. Another problem would be if you start with 2.97 times 10 to the 22nd atoms of molybdenum 91, how many atoms will remain after 62 minutes? The half-life is 15.49 minutes. So we have to figure out how many half-lives we've gone through. So we take 62 and divide it by the 15.49, and we'll find that it's 4 half-lives, so it's 1/2 to the fourth. We're going to start with our original number of atoms, which we can do. We don't have to always have grams, and multiply it by 1/2 to the fourth, and solve for our answer. We end up with 1.86 times 10 to the 21st atoms. Again, make sure that you can plug those into your calculator and get the same thing that I got. Nuclear transformations. Over the years, many nuclear transformations have been achieved. We can use particle accelerators, which are devices used to give particles very high velocities. And particles at very high velocities can overcome repulsive forces of the nucleus and allow things to transform. So before 1940, the heaviest known element was uranium. In 1940, neptunium was produced by bombarding uranium with a neutron. And since 1940, the elements with atomic numbers greater than 92 have been synthesized. So those are our man-made elements, and we call them the transuranium elements. So that's all we're going to cover on nuclear knot, just a little taste of it so that you have an idea of what it is and how it shows up in chemistry. Of course, there's a whole total branch of chemistry dealing with nuclear chemistry, which we don't have time to get into, but it is another area that you could potentially study.